All right. Yeah. So I'm Adrian. I realized I was talking before I didn't even introduce myself. Oh, and I can take my mask off. I'm Adrian Pricewell, and I'm an associate research scientist here at the CCA. And I'm also one of the coordinators for the Astropy project. And so I was asked to give a talk here, and sort of the aim of the talk or the context behind it is to share some lessons that I've learned about building and sustaining community software projects with the thought that many of you will contribute to or help to coordinate the link framework software efforts. And so I'm coming from the perspective of someone who's involved very early on in the Astropy project and has kind of transitioned into a role, more and more responsibility and more leadership in the project. And so this is kind of the overview of what I wanted to talk about. I thought just to set the stage, I should give you a little bit of info about what is Astropy, in case you're not as familiar with the project, a little bit of the history, talk about the community of people who develop and maintain the different software aspects of it, and then I'll get to the lessons learned. And one of the things I should say is it's funny hearing from Andy and many of and Rachel and many of the people here about the link frameworks. A lot of the lessons learned I'm going to say, I'm happy to see that LSSC and Link are already thinking about them a lot and paying a lot of attention to it. So that's great. Cool. So to start off in one sentence, what is Astropy? So this is our vision statement. This is on our main webpage. I think it succinctly explains the project. So the Astropy project is a community effort to develop a common core package for doing astronomy in Python, and also foster an ecosystem of interoperable astronomy packages. And that's an equally important part of the project. Now, Astropy has been around, I was shocked to realize, for over 10 years now, 11 years. But it is still sort of recent history. So I wanted to go back to the beginning and take you through how things started, because I think it is actually important context for thinking about creating new community software projects. And so to understand this history, we have to go back to 2011. If you can remember back that far, I can barely remember like what was 2019 like. But anyway, 2011, the software landscape in astronomy research was very different from the way it is now. So this is just a plot showing the full text mentions in using ADS queries for any refereed paper as a function of year for these different programming languages. And so you'll notice that back in 2011, by about a little over a factor of 10 or so, IDL was very much the dominant programming language, but there was still an early group working in and gaining momentum in terms of contributing to and sort of laying the groundwork for working on astronomy in Python. And so at this point, already in 2011, there was really a growing voice of people that were promoting Python as an open source and free alternative to IDL, which had very costly licenses. And primarily that was because it enabled more students and other people to participate in research if we can use an open and free tool rather than having to be tethered to a university with paid licenses and so on. Now, meanwhile, that's not the whole story. There's actually a lot of connections between early Python scientific development and astronomy already, which many people don't know. But actually, the precursor packages to NumPy and Matplotlib had heavy connections to Space Telescope Science Institute. So there were people there contributing to NumArray and to Matplotlib even before 2011. But anyway, at the time, even though there was that early effort in these sort of core foundational packages, there was a lot of missing core science functionality. You couldn't just do FITS image processing in Python at the time. And so that motivated many separate efforts, many different people who wanted to bring that functionality into Python. And so there was kind of an explosion of many different Python packages that all shared very similar functionality. Like if you want to convert your galactic coordinates to equatorial coordinates, I think there were like 8 or 9 different Python packages you could use at the time to do that. And so forward. So that motivated after someone in a sort of benign way announced another package that duplicated some of that functionality on a mailing list, this Astropy mailing list, which existed even before the project existed. So they just, announced their new project, their new package, and it got this maybe infamous email message response from Marshall Perrin Uh, the gist, you can read it if you want. It's kind of funny. I truncated it a bit. But the gist of it is that we're doing a disservice to the users if we provide a very confusing landscape of different packages that they could use, depending on what they install. As a community, we should be coordinating our efforts around a shared infrastructure and then building out from there. And that, remarkably, that maybe this is the only instance in time when a reply all to an email thread produced something productive, but remarkably, that email message was the genesis of Astropy. I think there was something like 30 or 40 different people replied to that email message and started coordinating around this idea of building a shared sort of centralized infrastructure that has the core functionality we need, with then later on the idea of building out from there. But I want to highlight just a couple important things that were also recognized early on. One is that it was realized that we can't just build another astronomy package and then expect everyone to switch to that. And there's of course a relevant XKCD for that. Give you a second to read it. Yeah. So if you just build another standard, then you're in a state where you have another standard. That doesn't actually gain the consensus and the network that you need. So we realized early on that we had to build the community in a way that people were deeply engaged and wanted to advocate for the package and develop and use the package themselves. And another thing we realized early on was that something I mentioned before, something that Python actually brings, which is that openness enables accessibility. So being able, just the fact that anybody can go out and download Python and install Astropy or these packages is the first step towards building inclusive research environments. And I want to just note explicitly, though, and I'll talk about this a bit more later, that doesn't guarantee those things. It's just the first step towards enabling them. So who was involved in developing Astropy, the actual code and the other aspects of the project? In the early days of the project, it was kind of a 50-50 mix of volunteer effort through grad students. So I was a grad student at the time, postdocs and community-oriented software engineers, but also an equal number of institutionally supported people at Space Telescope Science Institute or the Chandra X-ray Center, Gemini Observatory, and some other observatories. And they were allowed to use some of their science or support time to contribute to the project. So it was kind of a balance of indirect institutional support and a lot of community and volunteer effort. Wolfgang, I just noticed is here, was involved in a lot of that early discussion. So anyway, so even from early on, a lot of the decisions that we actually made through consensus of that group of people. And so it was thought of from the beginning that community engagement and getting consensus amongst the sort of heterogeneous mix of people that we had, that was really important. But one of the interesting things, and something that will come up again later, about having this kind of group where you have a lot of volunteer effort in your community, is that most of the development time just then naturally gets done by people who have an interest in developing a given thing. We can't actually tell people what to do because you're volunteering your time. I can't say work on io.fits in Astropy, which is something that almost nobody wants to do. And so it was very much a duocracy. The things that got built from the beginning were things that people needed for their applications or for their mission that they were supporting. Despite that, somehow we did still build a core package and a lot of the shared infrastructure that led into the project. So returning to this plot now, showing the other half, what does the landscape look like today? So about 10 or 11 years later. So Astropy was started around 2011, our first release in 2012. And since then, the landscape has completely changed, essentially. IDL has sort of flattened and started to wane a bit, and Python really skyrocketed in popularity. I think something like, this is for all referee journal publications, so something like 10% of articles reference Python in them. So Python has become very popular on a finer scale. Astropy has also become hugely successful and very widely adopted. There's a lot of different metrics that can show that, and I'm definitely not bragging. This plot actually just like blew me away the other day. So this is the fraction of AAS journal articles that cite one of the Astropy papers over time. And so we're basically going to hit about 20% this year, which is 1 in 5, which is, I was like, what? Anyway, so that's pretty ridiculous. So today the project looks a lot like we imagined in that initial vision statement that I showed you at the start. And so it's not just the package, the thing that you get in Python. That's the core package. That's one sort of pillar of the project. The project also refers to the software ecosystem that's built around that core package. So we have a lot of these, what we call affiliated packages or infrastructure packages that expand on that core functionality and bring it into more subdomain specific applications. And then importantly, a third equally important pillar of the project is the community. So this is the users and the developers, the communication between them, educators who want to teach with Astropy, and all of the educational materials that we produce as a part of that, we want to be able to share broadly. And so this has been a really important focus of recent years is building out the community infrastructure. So the community now looks a little bit different than it did at the beginning when it was mostly volunteer effort. We still have quite a bit of volunteer effort, but we now at least have a formal governance structure and different bodies that have power within the project. So we actually only last 2 years, I don't know what year it is, 2 years ago maybe, we formalized our governance model. And so we have this voting body, voting members, which is anybody with a named role in the project or who contributes significantly. We have the coordination committee, which I'm on, which is a small group who are supposed to sort of take a bird's eye view of the project and just kind of gently coordinate. Again, we can't really tell people what to do, so we're mostly delegating and trying to get people excited about doing things. And then we also have a finance committee, which is a group of people who oversee and disperse our finances, which is an exciting new thing that we have in the project. Besides that, we've also grown the community in terms of the number of ways that you can contribute to Astropy. So at the beginning, it was basically, build infrastructure, write code, write documentation. Those were kind of the main 3 ways that you can contribute. Now we have many other roles and many other ways that you can contribute. You can, you can of course contribute features or development time. You could contribute a tutorial. You could write a tutorial text or coordinate a workshop or even copy edit our documentation. There's many different points of entry now that don't involve actually writing code. But one of the interesting things is that despite this formal governance structure and despite the fact that we know we have a bunch of named roles and we have many different ways for people to engage, we're still largely driven, not completely, but largely driven by volunteer effort. And so that means that, again, we can lay out these things and say, we think it's important to do this, but ultimately then it's up to the community whether or not to implement those things. And so that's something I want to just highlight is very different, I think, from the way that the link frameworks, the software aspects might work. I don't know, we can discuss that later, I guess. And so that's been a natural part of what aspects of the project have expanded rapidly and which ones haven't gotten as much attention. And yeah, I just wanted to briefly note that this probably will change a little bit soon, although we're trying to figure out the details. And that's because we now have funding. And so that's a relatively new thing, that the project itself has funding rather than individuals who are working at an institution and contributing their time. We now have, as a project, some fairly large grants from the Moore Foundation and from NASA that we can, in principle, use to hire people to work on specific projects. Problem is we're just working out how to actually do that because there's a lot of logistical reasons why the people that we need might not be in career positions where they can actually contribute that time in a way that ensures that they will have a career after they do this work. So this is a big outstanding problem, I think. Right, so that was a lot about Astropy. I want to briefly emphasize, though, that Astropy and Python usage in astronomy in general are really just parts of this really active ecosystem of packages in Python. And so I like to think of it kind of like a core section of the Earth. So Python, of course, is the innermost core. That's kind of the foundation. Outside of that, you have the core utilities that build out the language and enable a lot of the numerical analysis that we do, like NumPy or Jupyter, et cetera. On top of that, you have what I call the scientific foundation, could be whatever. But these are things that add, visualization and model fitting and data structures, things like that. And then the outermost layer here, the core, that adds the cross-domain, more specialized, but still cross-domain tools. Things like machine learning or image analysis or symbolic manipulation, things like that. Now, of course, a lot of times I've seen images like this before. In fact, Jake Vanderplas, I think, was one of the first who made one of these kind of ecosystem graphics. But one layer, oh, right. Also important to note, this whole layer of the stack has been embraced by industry. So there's been a lot of effort within Netflix and Google and Facebook to build out some of these tools. But there's also the surface of the Earth. And that's where I've put these domain-specific tools. So Astropy, GeoPandas, YT, et cetera. And I put them on the surface because I actually think that they're more like trees. So now this is the part where I start to really abuse the analogy. And Katie is going to start cringing because I tried this on her before, and that's what she did. She's just sinking further and further into her chair. But I actually think it is a useful analogy to expand on a little bit. And why are they trees? Because these domain-specific projects that live on the surface are really their own mini ecosystems that are deeply connected to everything below, but which expand in fruitful ways. Ooh, there weren't too many cringes or puns there. So let me further make you cringe. So if we imagine the Astropy project as one of these fruit trees, then the core package is sort of the trunk and the root system of the tree. The affiliated packages that I mentioned and the infrastructure packages, these are like the branches of the tree that come out of the core, out of the trunk. And then the research projects, those are the foliage and the fruit that the tree produces. And so we often use the word ecosystem a lot here, but I truly think that this is a good analogy because it really emphasizes how interconnected everything is. Obviously, if the core of the Earth imploded, that would mean bad things for everything above it. But also, if the roots of the tree started deteriorating, that would also lead to a lot of rot going up. You need to make sure the whole system is happy in order to produce the best fruit or the best research projects. And so ideally, you want, sorry, I put those arrows there. Ideally, you want collaboration and contributions that go from the top all the way down into the core. You want to be able to push changes and help upstream from even as low as the research projects.
You didn't take it far enough. There are fruits growing on the trees. They become pulp and that becomes paper, right?
Yeah. I'll put my talk in a GitHub repository and you can open a pull request. Good. Okay, so that was a lot about Astropy and the sort of astronomy ecosystem of software packages. So I now want to just kind of briefly summarize some of the lessons that at least I've learned along the way. I don't know that everyone in Astropy would agree. One is that people contribute to community software with many different motivations. And so what do I mean? So within Astropy, people, like the reason people come and make a pull request or contribute a tutorial span all of these different things. And I'm probably even missing some. So for example, people need to implement the functionality for their own research project, or want to build a tool for their students to use. They think it's fun, or they participate through Google Summer of Code. And again, this is probably just a partial list of the real motivations. But the point is that this is a diverse set of motivations. And I actually think this is really good. I think this is a pro, not a con. I think that ultimately this will lead to sort of better coverage of the needs of a project because different people want to get different things out of the contributions that they're making. On the other hand, I think it's important to acknowledge that the culture of a project, of a community software project, is sort of directly reflected or influenced by the balance of people who are contributing with these different motivations. And so that means that your culture can evolve. and will evolve probably as that balance changes. But it also means that you can actually coordinate the culture of your project through these means, because you can create rewards or incentives for contributing in certain ways that draw more people in through one of these motivators. So, for example, within Astropy, we've tried to support some of these motivators. We have a team page where we list names of people who are in named roles in the project. Sometimes they say unfilled. We add long-term or lifetime contributors to a separate credits page with a little bio. We write papers. We invite all of the contributors, anyone who's ever contributed to Astropy, to be on the papers. They are good for your citation count. So that is a plus for people to join in. Some people contribute just to be on the paper, I'm sure. And then we also try to label our issues in our different repositories in a way that make it clear what entry points you can come through if you want to solve one of these issues. So, for example, here I just selected everything that says good first issue, which are where we send people, new contributors or people who are being mentored into contributing, or summer students, Google Summer of Code students, etc. So that was the first one, and I'll come back to it in a minute. A second lesson that I think is really important that we were starting, wherever Mario is, we were starting to talk about this a little bit at lunch, actually, which is that I think there's a lot of really important but under-supported roles that are in between roles. And so that's a really vague and general thing to say. So let me give you two examples. So one is that there's a spectrum from software engineer to astronomy researcher. So it's not like they're these two disconnected things and then discussion in between. They're really overlapping, and there's a whole spectrum of people with expertise and interests in between. And I think personally that it's critical to actually populate all areas of that spectrum if you want communication and you want a software project to work fluidly and in the best way. Another reason this is good is that it actually naturally brings in people with different motivations, because whether you're leaning more towards software engineer or leaning more towards astronomy researcher, that kind of naturally speaks to the last point that I mentioned there. And then, of course, there's the practical thing that we also started talking about at lunch, which is that there's not a lot of support for careers in this in-between space. So that's a big but to this. And of course, LSST is helping, but I wanted to just kind of challenge the field a little bit here and say that in the future, these positions might look different than ones that you might think of today, like 50-50 or 80-20 support and science roles. And that's because I think there's a lot more overlap between these terms than we acknowledge. They're not support and science, they're together. So that was one set of things where there's roles in between roles, from software engineer to researcher. Another place where this sort of vague statement applies is in the what's sometimes called user to maintainer pipeline. But it's the people who participate in a software project. So there's a spectrum from user to contributor to maintainer to coordinator in a project. So there's people who just use the code. There's people who use it and then open issues if it breaks. There's people who contribute bug fixes. There's people who contribute new features. People who do the maintenance work. And then there's people who coordinate the project. And in Astropy, there's people at all parts of the spectrum. And I think that a healthy community software project will really have people supported and feel good about their contributions at all levels of this spectrum. So sometimes in software projects, you hear, on the developer side, you hear negative things about people who just use the code or people who just open issues and never fix them. And I think that's a huge negative aspect of software culture right now. I think we need to be supporting the people who want to engage in any way that makes sense for them. And of course, this is also a pipeline. So part of it is then talking to the people who are engaging and finding if you can move them from user to contributor, or if they're interested in becoming a maintainer or a coordinator, et cetera. And so I think this has been really important for Astropy. Okay, and I'll try to go a little bit quickly through this, but I think this is equally important and something that I mentioned all the way at the beginning, which is that in a community open source, open development software project, openness does not guarantee diversity, equity, or inclusivity. And it sounds like everyone here is thinking about this a lot already. So I don't mean to preach at all. This is kind of a lesson that we've learned by failing, in a sense, which I'll talk about in a second. But really, this is because there's systemic reasons why just opening up a software project is not enough to get a diverse and group of people to participate in it. And part of that is that there's very heterogeneous and biased reasons that some people get training in software and other people's don't. There's also a lot of very complex technologies involved in contributing to these projects, and it's hard for any one person to get trained in all of these things, especially if you come from a underprivileged background. But then there's also a whole aspect of the community culture, the project culture that you have, which if you don't work actively to set, that's going to not allow people that you might want to engage with your project. So I just wanted to pick on Astropy a little bit and show a place that I think that we've failed. And I'm sure there's many other ways, but this is one that's been on my mind recently, which is in terms of geographic diversity. So the coordination committee is 5 people. 4 of the 5 of us are in the US East Coast in the Northeast. 1 is in Minnesota. So we're basically all in the US, very not representative of the people who use Astropy. And the voting members that we have are all pretty US East Coast dominated as well. There's some more distributed in Europe, but it's very sparse everywhere else. And so here's one way of looking at that. I grabbed our Google Analytics for the number of people who have accessed our documentation in the year 2021, and then plotted it over countries. And so this is just raw number of users per country for the entire year of 2021. The red stars, which are all in the US, continental US, those are the coordinating committee members. And the green stars, which you can see are, there's a lot of work going on underneath the Northeast there, but there's a lot of green stars under the cocoa stars there, and then many in Europe, and it's very sparse everywhere else. And so in particular, Asia and Oceania and Africa and South America are basically unrepresented in terms of our voting members in the project. I was going to show you one other thing, but I think I'm gonna skip through that. Basically, we also have gender issues, so it's like gender balance issues. So it's like astronomy 20 years ago. So anyway, I guess my recommendation here, which is again something that has been brought up a lot, is that you need to explicitly address these DEI issues from the start when you're founding a community. Otherwise, you're going to be playing catch up like us. And now, only in the last couple of years we've been actively trying to address these things. But now it's a very slow process if you don't, get in from the start. So let me skip the challenges since I think we're way over time. So these are those 3 main points with a couple of and a to do there. That's great. With a couple of good, excellent. To do. Anyway, these are the main lessons that I wanted you to take away. Some summary points from the discussion and an unfinished summary point. But I just wanted to have sort of one meta lesson that kind of contains all 3 of these, which is that community engagement is, when you're starting a community software project, obviously the software part of that is very important, but equally important, or maybe even more important, is actually the community engagement and community establishment in terms of long-term sustainability of the project. So now I have to put up our sponsors, but thank you, and we can do questions.
Two questions, but I can just do one. I'm sorry. So my first question is I'm curious. So when I interact as a user with Astropy, I know what I want my function to do, and so I can find the read the docs page for the appropriate function. But when I interact with like the Rubin Science platform, I'm just looking at a series of tutorials. So I'm wondering what your thoughts are on the gap between those two ways of interacting with the code and how users are contributing to either of those.
Yeah, I don't have an exact answer, but I do have thoughts in that space because I've been involved in our effort to build out our tutorials in Astropy a bit more, which is actually coming, which is somewhere that we share a person. Jonathan Sick has been working with us a lot on that. Anyway, yeah, I think from the beginning, back in 2011, people just thought, okay, you need to write documentation. So that's what we put a lot of our time into. We're now realizing that that is not, as a project grows, that doesn't scale well because it becomes this like monolithic thing that's impossible to find entry points into. So we're trying to create tutorials and things that explicitly duplicate the content that's in the documentation, but provide different ways of people to flow into to find the content that they need. And so we're deciding on sort of 3 layers of this information we see as the sort of API level, like what does every function, every class do? There's examples that are embedded in sort of the narrative documentation that enumerates everything that's around that API stuff. And then we have longer form things called the tutorials, which show use cases, kind of case studies. And then now we have a 4th category, which we're calling guides, which are compilations that like show a whole workflow. So an example of one that we have right now is you want to reduce an image using the Astropy tools. What are all the steps involved in doing that? So I don't think there is an answer because different people will engage in different ways. We just want to make sure that there's a many to many mapping from what people want and what they can find.
Well, let's see. Is anyone else got a question? Otherwise, we're going to give Ashley a second. Okay, one over here.
Thank you very much. I actually have more of a wonderful talk and summarized wonderfully the problems that you showed, or the challenges that you showed. So you over them quickly.
Use your seat mic, please.
Oh yeah, click your seat mic on.
Oh.
There you go. Yeah, there you go.
Wow.
Speak and you will be heard.
Anyway, so one of the things that I sort of like from a history perspective, and that's some of the things that I think you can really learn is like Space Telescope at the very beginning, like was the only sort of organization, and I'm so immensely grateful to them to sort of put in. I think Terry Greenfield was one of the people that was sort of in the back and he was sort of making these machinations. Then we got 3 FTs at the very beginning. And then 2 years later, these 3 FTs turned into 30 FTs. So he just invested a little bit of his infrastructure. And so to defend Astropy a little bit, we sort of said the voting members are not equally distributed. And specifically for Europe, at ESO, I told them, use Astropy. You need to support them.
But that reveals an important part of community engagement.
ESO's leadership was not interested in engage in open science at that time. And so it shows if you want to engage with the future of your field, you need to support these things. And I think Space Telescope and many people within, I'm sure Terry was one of them, did that and shepherd this forward. The other thing that I want to say, bureaucracy is a great thing because I think when you develop things for your own science, you know that it's good. And I think one of the reasons where the virtual observatory fell a little bit flat is it was given to software engineers, said make something that's great. And so they made things like ADQL, which are great, but it's not necessarily always something that is useful for a scientist. And so I really, really think the success of Astropy was people like you and many other people that were doing this for their own science. And you found it interesting in your science. And then essentially other people found it interesting in their science because it was something that was developed by a scientist. So I think this integrated thing that you showed at the very end, where you sort of integrate developers, where you don't separate science into what people believe science is and what people don't believe science is, but we're saying all of this is science.
Yeah.
That is the future. And I think we really need to build on this. But I think it was a very nice talk. And thank you so much for summarizing. I'm going to disengage. Does this work?
Are we going to go 5 minutes over? Do we take 2 more minutes? Are we allowed to do that? Rachel, shall we? One more.
Use your seat mic, please.
I think Knut had his hand up first, so let's take Knut.
Thanks for so beautifully laying out the ecosystem of Python and Astropy. So does the scale of the ecosystem make it harder to move on to another sort of base language should something much more efficient come along? And maybe one of the one of the things that perhaps made it easy to move on from IDL, besides the cost of the licenses, which I think was huge, was that there wasn't the same level of ecosystem and community built up around it.
I think that obviously, well, okay, so Julia is a special case. By the way, Julia is on here. I just did a full text search, which means that people named Julia here. Which I was hoping no one would ask, but anyway, but that basically means you can divide by 7 or whatever, or subtract 7, I guess. And so Julia is really where Python was back in the late 90s, I think. Anyway, for Julia specifically, and some other languages that are conscious of the fact that Python is popular, they're building in ways for you to interface with other languages. And so there you go, that kind of answers your question. But I actually don't think Python will go the way of IDL, at least as I'll be back here in 20 years being like, damn it, I was wrong. But anyway, I don't think it'll go exactly the way of IDL because for a couple of reasons. One is Python is used in industry, and so yes, that can change. But right now, there's a lot of investment outside of astronomy, which is important in terms of Python development. Whereas at IDL, it was like if you want to fire missiles or do astronomy, you would use IDL. So there's a little bit different. There's military contractors involved. Anyway, Python is also very much a glue language. So I don't just use Python now. I use Python and C and C++ all from within Python. So I think that naturally also leads you to like, okay, let's say Julia becomes a really great resource that's better than C and we want to support. I guarantee there will be much easier ways of interfacing with Julia from within Python. So I don't see it in the next like 5 to 8 years going the way of IDL. And I support using many different languages. But yeah, it's an interesting question how that relates to Astropy.
Okay, so I'm representing the image analysis and classification group. So you can see here we answer question 2 and 3 together in this giant table. The science use cases in our group ranging from lensed quasars, classify galaxy morphology, trying to classify transients host galaxy, finding slow transients, comet in the solar system, estimate distance for dwarf galaxy, nearby dwarf galaxies, debugging artifacts for weak lensing, and search for resolved dwarf galaxies. This is within the Milky Way. And so you can see most of these science cases share a lot of similar functionality. The most prominent one, including people want to be able to link the image analysis with other archival data, archival imaging. Everyone wants to be able to do the analysis on postage stamps, and that can be ranging from like 10 second to 10 minute sizes. Most of the transient-related analysis want real-time analysis and having some machine learning-based variable clustering, like clustering light curve, for example. And most of the static science cases require doing machine learning-based clustering on static image, and also some way to do visual inspection and even citizen science. As an additional kind of bonus, we also list the data product we might need on the leftmost column. If we go to the next slide. So we then brainstorm based on the functionality that we list on the previous slide. We kind of brainstorm which software exists today. And so you can see we group them into several categories. There's several software that we can use for deblending or remeasuring the photometry. For linking to archival data, the VO interface is one of that. There has been a lot of Astro specific machine learning software for variable and transient, which we list here. For static one, we list on the last bullet point a few general purpose machine learning softwares. And obviously, we also need to be able to generate postage stamp and do visual inspection. So the main limitation for existing software, including, well, I guess, let me put it another way. So the main requirement for this using this software, including need to be able to work with remote data, need to run at scale, run in Python, Jupyter environment in the cloud, and they should work with multiple data formats. And then one important one is that, since we have so many general purpose machine learning software out there, how do we incorporate those software into the astro-specific analysis? Obviously, people want to store this data. I think our most stringent storage requirement would be the comic search, which may generate about 2 terabytes per night of cutout images. Those are intermediate data product that doesn't need to be stored like for long, but we need to process those data in a short amount of time and need that storage during that processing time. And we need to think about whether regenerating some of these data product may be cheaper compared to storing them. Yeah, that's it.
Thank you. Any questions or good to move on? Cross matching, Mario.
Cross matching. Almost all science use cases, I think all science use cases needed this technical case. We talked about what functionality is needed. Can you refresh it? I think there's been a late change. Yeah, we find that there are two levels of functionality that we need. One is real-time cross-matching, so things for think alert streams, and the other one is large-scale static sky cross-matching. So for real-time, people were talking about multiple or cross-matching to get multiple, let's say, an order of n equals 10 neighbors within something like 5 arc seconds, with latencies at alert scales and the number of objects similar to the number of alerts. So the idea is, as the alert stream is coming out, you'll want to match those, cross-match those alerts to catalogs that LSST doesn't natively cross-match to. These are going to be multiple catalogs depending on science use cases. They're in that sense they'll be arbitrary, because sometimes you may want to use one, sometimes the other. And the interesting thing that came out is that there will be a choice of distant metrics. So typically when we think of cross-match, we think about things that are near on the sky in terms of how many arc seconds distant something is. But ZTF experiences showed that actually computing real space distance is quite useful in discriminating like which object is related to which one and which object originates from what galaxy. This type of information is most likely to be added by brokers. They could enrich the alerts with this kind of information. So we need connections to broker teams to see what's being done in this case. And Leanne reported that essentially all of them are very interested in working on this type of use case. The other use case is static sky cross-matching. So generically, think of this as cross-matching order of 10 billion. That will be LSST, to order of 1 billion. That would be everything else catalogs. Here, one would want to do this for all the use cases that we talked about, roughly on monthly scales. But ideally for exploratory tasks, you want to make that as close to interactive as possible, example, with smaller subsets of catalogs. An important feature that came up here is subset matching. So do not just take 2 large catalogs and cross-match them directly, but say, for this 10 million objects, get me the 3 nearest neighbors that satisfy some criterion. Let's say G minus R less than 0.5 or something else. And this actually makes the problem technically much, much more difficult, because the way you would index this changes a bit. The other things that were brought up were probabilistic cross-matching. That would definitely be super useful. It may be emulated if n nearest neighbors are returned. That way you could do probabilistic cross-matching functionality as an afterburner. And the third thing is reporting non-detections can be extremely important. For transients, variability, for solar system science, like knowing that an object has not been cross-matched to something else in a certain region is quite information heavy. And this is related to also having reliable selection functions computed on the LSST. So would LSST have actually detected something at this point in the sky, or is this point in the sky, what's the probability that it's falling between the chip gaps? What software today exists to generate these analysis? We didn't have really much time to discuss, but there's clearly a lot of existing work and as well as plans from the broker team. So this is something to be investigated before any new work is done and definitely coordinated. The functionality that's missing from current tools and algorithms and infrastructure, I think, is largely on the scalability side. So being able to do large cross matches, being able to do cross matching fast to keep up with the streams. The other big thing is cross matching is not the end; it's really the beginning of science analysis. So the next thing you want to do after you cross match two catalogs is to pull additional data from both catalogs being cross-matched and then feed it to some code to do something scientifically useful. And this is a bit that's missing right now in large part. The way to think about cross-matches is they're really just complex joins between large tables, large catalogs, and right now the catalogs are distributed. So if you try to, join something with cross-matching, so let's say the LSST that lives in California and the catalog that lives in Europe, how would you do that? Because it's not just knowing which object is which, it's also pulling 100 columns from one catalog and 100 from the other and then doing something useful with it. Does this generate new data products that need to be stored? Well-known catalogs should be pre-matched. That's definitely things like LSST will already we heard that it's likely to be cross-matching to Gaia and make that information available. There may be n order a few catalogs to which it will be just useful to pre-compute this and store cross matches. And there'll be new general use case catalogs of, for example, AGNs or specific types of variables that you might want to pre-cross match to. But in terms of volume of data products, we haven't estimated it, but the cross-match tables themselves are likely on order of terabytes. They're relatively small. They'd be valuable to compute, as we said, in 6. The problem here, or the challenge why that's not enough, is that new catalogs keep being created, and more will be as LSST is ongoing. So keeping an order of n² cross-match tables may be challenging, not just for us, but the community as a whole. But importantly, that wouldn't satisfy the quote-unquote subset matching use case. So for these objects, give me n nearest neighbors satisfying the following condition. So the underlying, I think, after all this discussion, I started thinking about this, that the underlying problem is really how to do distributed joins between large tables, large catalogs, rather than just cross-matching in itself. It's the next step. How do you go from cross-match to science? That is sometimes quite challenging, especially with large-scale cross-matching. So this is sort of when we ended up. And if there was something that there's some combination of tools that can do what's in bullet point 3, I think we would enable all these use cases that brought cross-matching up as an issue.
Okay, so for the image processing, we found that there were science use cases basically across all of the different areas, but I'm not going to go into them fully, but we have put them up here. I think we can go directly to the next slide. So focusing more on the functionality that's needed for all of these cases, and they're grouped pretty nicely into a small number of different functions. So a big one was image stacking over various timescales. So this is something that's where it's not requiring any kind of new code, but just different combinations of data that are used for the standard coads. And then there was also more custom stacking where you'd actually have shifted stacks. So that would be like following solar system objects that have strong proper motions. Also, you'd need, like, for some cases, they're oddly shaped coads. So we put a couple of examples here on the bottom, where on the left you have the stacking shifted objects, and then on the right, an example where you actually need a big cutout to do analysis on these objects where you have like a faint trail of some extended nearby object. Another thing that came up for a few different science cases was reconvolving LSST photometry so that you could combine it with external photometry. This is another one where we think a lot of the code is already there, and it shouldn't be too complicated to do, but might take some computing. Custom deblending was another big thing where, I mean, there's a lot of existing work on deblending inside of the data management team, but for specific cases like gravitationally lensed quasars, they will want to go back and redo deblending for these specific use cases. Other general just custom photometry on cutouts. And then for type 1a supernova, people will actually want to do scene modeling and do a model of the time varying point sources on the like suite of cutouts around a specific or on this location of the type 1a supernova. Next slide. Okay, so we mostly thought that the software exists for these right now. So for deblending, there are a lot of algorithms out there, like Scarlet is already being used in the data processing. There's Beast, Gap, and there are a few different existing codes for doing the lens modeling. For the various needs for image cutouts, the image cutout service that I guess there's some uncertainty about what services will be already provided, but we'll need both image cutouts on the coads and individual visits. There's ZUDs for doing custom stacking for transients from ZTF. For some of the solar system work, there's existing GPU code, but we thought that that's going to need some work going forward just to make it more efficient and fast. And then for scene modeling codes, there are things like Tractor or Scarlet that exist and that could be combined with some of the components that we already have from the data processing to do the scene modeling. So for things that are totally missing, we thought some things might be needed for galaxy fitting. Like you might have situations like a bright AGN on a diffuse galaxy, and that might need some tools that are not currently available. For the data products, most of these create fairly small, well, hopefully, data products of small quantities. Like for the supernovae, you'd have light curves, and that's order of a million data points for 10,000, 100,000 supernovae. Potentially postage stamps for all of those, which gets to be more volume. Then you have like catalogs of lensed quasars, potentially lensed galaxies. Most of these are catalogs of pretty small size, and then potentially stacked lens images. And then for the solar system objects, you have oddly shaped cutouts. This is the one that gets really big, where you'd maybe have 100,000 to 1 million objects per night, and you need cutouts for those. So for the volumes, most of these are fairly small, except for those cutouts that could be an order of tens of terabytes. But then, so that's for the final products, but there is some uncertainty on the intermediate data products, like having all of these cutouts when you're doing the stacking, that might make the processing take up more memory in the processing. Sorry.
Matthew.
Okay, so original time series, we started off by sort of doing a brainstorm of the science cases that need this technical support, and it's fairly across the board that all of the groups sort of put up their ideas and whatever, and so we then rotated that round and tried to identify common areas of functionality that each of those would feed into. And so we came up with this master list of visualization, anomaly finding, feature extraction. I should say we voted on it as well, because we can't cover all of those. And so we put those all up and then did 5 votes per person who was there to figure out which ones, and 2 people online to figure out which ones we would try and focus on. We managed to focus on 3.5 of them. But you can see the list there: visualization, anomaly finding, feature extraction, statistical representation, period finding, parametric fitting, classification, follow-up, tabulation, forecasting, online learning, active learning, ancillary data. And so, can you jump to the next slide? That's the result of our individual discussions of each of those. So we did a 20-minute sort of focus on each of those to try and identify, for example, what is visualization? What are the common things that we want for visualization of time series in each of our respective science areas? What types of visualization? So, for example, what would we want to visualize? Raw time series, periodograms, associated data, features that we might be extracting from that sort of thing. We want to do it in an interactive fashion. We want to be looking at individual time series as well as populations of time series. We want to be looking having some coupled plots like Leanne was showing this morning with bokeh and holosuites, that sort of thing. So those are the sort of ideas. So we were brainstorming each of those, and so the 3 that we managed to cover, the 3.5 we managed to cover was visualization, then anomaly detection. Again, what are the algorithms people currently using? What's their current approach? What types of things do we want? What are the problems that we're facing? And then also for parameter and statistical method, parameter fitting statistical methods, feature representation of time series. Again, what are we doing? What are people doing in the variables group? What are people doing from the transients perspective, or what do they want from that? What do people want from extragalactic versus galactic variable type approach? And so, with those brainstormings going on, we then sort of try to identify what are the technical areas or the common technical areas where we think some sort of effort would help. So can you go back to the previous slide? Thanks. So, I mean, the general story is that for a lot of these things, there's a lot of software actually already out there, which are people using in their own domain or subdomain or for addressing their problem. But there's maybe no common ecosystem or a data model, which is, one of the things that might improve our ability to work in a common ecosystem, or that level of abstraction might allow us to better then identify ways of speeding up particular algorithmic, let's say inverse matrix. If we know that the data is always going to come into in a specific form, we can focus on doing some sort of algorithmic thing, and then you can layer on top the additional calculations you need to work on that. And there are some things which already have in the ecosystem out there, Lightcurve for test stuff, DBScan for other things that sort of have some underlying, but maybe we should be thinking about that. What functionality is missing from the current tools and stuff that's out there? Scalability, I think, was common across the board. We want to be able to do not 37 billion time series, but certainly, a large number quickly, both for visualization and analysis. Running the same analysis many times, maybe if you're changing data points or adding data points or improving things like that. And again, this idea of a common data model or API that would be efficient for large scale analysis, and also just dealing with the fact that the time series are not nice and regular sampled. These are going to be noisy, gappy, irregularly sampled, heteroscedastic. So, how do we do that? And how do we ensure that the algorithms are running properly with that and with posteriors where they're needed? does this generate new data products that need to be stored? Yes. Classifications, features, anomalies that are identified for follow-up, annotations that we might want to make onto time series, that sort of thing, which will then inform downstream. And again, the volume, as I say, potentially you might want to run at least once a year overall, 37 billion in a data release. But actually, you might want to run on smaller subsets on a fairly high cadence nightly, potentially, for, let's say, all AGN, 20 million AGN on a nightly basis to do some feature amendments, so we can track what the population is doing and then identify the anomalies for fast follow-up and things like that. Again, visualizing the results, saving classifications, updating. So, the amount of data that you may potentially be working with, particularly if you're looking at a population type analysis, where you may have, several million in the data set that you're looking at and scaling in and zooming in, scaling out and manipulating that. So the sort of problems there, or the volume of the problems that we're thinking about. And we did start on parameter fits, but then we had to go upstairs to freeze. So.
Yusra, selection functions.
All right. So what science cases need this technical case? All of them. We had pretty good representation from the various science breakout groups. Some notable absences were the transient group and cosmology groups. We tried to represent them. We found that most of the selection functions needed fall in a hierarchy of very low level to high level, or very general to science case specific. On the low level general side, everyone needs point source detection efficiency in both the deep coads and also the single epoch difference images. These use cases are so general that the Rubin Science pipelines are planning on providing data products to fulfill these. We're providing heel sparse property maps. So that's the, for example, 5 sigma depth as a function of heel pixel for coads in both the single epoch difference images. It's cheap to make additional maps of different quantities that are needed. Also, that's also going to be cross-validated via injecting synthetic sources. On the very, and we're also, so there's going to be the very general use case of injecting point sources and very simple galaxies, but then there's going to be a very science specific case, synthetic source injection as well. So then on the very specific high level science case side, we've talked a lot about different classification algorithms. You can go to the next slide. Different classification algorithms and different very specific detection algorithms during this workshop. And for every one of those algorithms, they will need a selection function to go from the population that has been classified to what is actually out there, the number counts or the rates of the supernova or whatever. So some examples of these is if you're classifying AGN based on their variability characteristics of their light curves, in order to convert that to number counts, you would need a population of simulated AGN and light curve properties to pass through your classifier to get that selection function. For another example for a detection algorithm would be, what's your probability that a diffuse comet would need to be detected? In that case, you would need to simulate a population of comets to inject into your images. So the pipelines is providing a framework for injecting different types of images. You can inject your own images. You can also inject catalogs of point sources or galaxy properties you can pass to GalSim. But they're simulating these populations of specialized objects are very science case specific, and there is part of it that will always be science case specific and not generalizable. And I think that's our summary.
Okay. Actually, can you reload? Sorry.
Sure.
I think it's only a minor change, but
You can actually write so clearly on the blackboard it comes out.
okay. So for photometric redshifts, this is just context before getting into use case. So the assumption here is that the Rubin data releases will have one particular PhotoZ algorithm, for all the objects. And then people are always going to be interested in exploring different algorithms, maybe ones specific to some science case, or maybe like new potential algorithms that they're going to propose for the future. So there's everything that we're going to talk about. It's something that would be of interest for like more than one set of redshift estimates. So we found some relevant topics that we're going to ignore for now, but things like cross-matching to infrared data sets to improve the PhotoZ, impact of prior information and training, computational efficiency. This is important in the landscape where there are like multiple redshift estimates people might want to use. So some of them might not work at the at LSST scale. So we tried to identify some broad areas of PhotoZ infrastructure that cut across a lot of different extragalactic and cosmological science cases. So we focused on 3. One was on how the photometric redshifts are represented and stored, which can have a big impact on the costliness of the analyses that you're doing with them. That's especially important if it's not just a 1D PhotoZ PDF, but like a joint PDF of PhotoZ and something else like stellar mass. The second one was about uncertainty quantification. So meaning if you have a PhotoZ PDF, forget about truth for a second, just like how accurately does that algorithm think it's estimated the PhotoZ? Like is the PDF multimodal? Or is it a single peak? If it's a single peak, is it really narrow? Is it really broad? So how well does it think it know the redshift? That can be folded into things like sample selection or classification algorithms or other parts of the analyses. And then the third area is science-driven metric infrastructure, meaning if you have some PhotoZ PDFs, there are often some basic statistical accuracy metrics like what is their bias with respect to the true redshifts, or what is their scatter with respect to the true redshifts. But many science cases will have science-specific metrics, like because they have to do specific things with the PhotoZ, and depending on how they're using them, that will impact their science in a different way. So and again, in the context that people might have different PhotoZ methods that they're proposing for different science cases, it's valuable to be able to compare these and have some common infrastructure. So it's not just that somebody has their favorite PhotoZ method and they can report one science-driven metric for themselves and not talk to any of the other science cases. So there's a use case document for each of these 3 things on the right. And rather than trying to go through all 3, the next slide is just walking through the uncertainty quantification. So, we found there are a lot of extragalactic and cosmological use cases, more than I want to list on this slide, but there are a bunch in the use case document. One thing I do want to flag is that the actual quantity of interest, like how you quantify the uncertainty, might differ for some of these use cases. Like some use cases might really care to know if it's a bimodal PDF, whereas for others it might just give me some variance, and that's fine. So the functionality is essentially the ability to rapidly quantify like a meaningful statistic of a PhotoZ PDF for like 1 billion objects, potentially with multiple PhotoZ PDFs like from different methods. So this is primarily, I think, an issue of running consistently some calculation at scale for a really large sample, but also on broker filtered extragalactic alerts. So that would be like more frequently, but a smaller population after filtering through a broker. Individual PhotoZ codes often deliver some point uncertainty estimate, but the actual, like what they report and what it means is not at all standardized, which can be challenging if you want to compare them. So the Rail, which is a public desk code base, can talk to multiple different PhotoZ codes and could easily be modified to calculate some requested uncertainty estimates from PFZ in a self-consistent way across those PhotoZ codes rather than relying on whatever the codes choose to report. So functionality that's missing. So if individual PhotoZ codes, it seems unlikely that they're all going to get in sync. So we thought about Rail, and it should be pretty easy to implement specific choices of uncertainty estimates in that context. We'd have to check that it works at the scale that we want. In terms of new data products, unlike some of the previous use cases, this one is not scary. Yeah, it generates some new data products, but they're modest compared to the data volume of the PFZ for the objects of interest. So if you're trying to store 100 numbers for a PFZ, adding a few point estimates per object is pretty small. So we didn't really estimate a volume. Just we think it's not a big deal.
Is there one? No, that is it, right?
That's it. Yeah.
So that's one. And there's 10 minutes left. So do you have some closing out for today, or anything for tomorrow? Winters, or do we just go and start?
Remind that there's a reception right
now. We saw the cupcakes. We were told we can't have them until after 5. So we know there's cupcakes. So are we just going to reception? Anything else?
Well, I mean, maybe we could give a few minutes if anybody has any comments on or questions on it.
He had his hand up, so I don't know.
Group, the image that was shown, which showed a streak, and at the end of the streak was an object. What was that?
You mean this?
Yeah,
one?
this one. Yeah.
So there's a tail on this.
Right.
I can't see it.
Yeah, it's a.
I can see it on my screen, but I can't see it on this.
Yeah, I can see it from here. So I guess you have to be away from it. So do we know what that is?
It's a main belt comet.
So it's a main belt asteroid that's showing dust emission coming off, and so the dust is aligned in the orbit plane because dust falls into the orbit plane, and then we're seeing it edge on. So that causes the tail.
That's good.
I think the point was that this was one of the drivers for getting very odd shaped long cutouts.
Yeah.
So we can get an object like this. It's kind of nice. Mario? Go ahead, Mario.
So a question for the selection functions group. So the selection functions that are going to be provided, or the efficiency, I guess, that is going to be provided, detection efficiency is going to be provided for the single epoch data. Next slide, I think. Yes, so single epoch level depth as a function of position. Does this mean that, will this include things like, for example, there's a, I don't know, 9th magnitude star there, so this part of the image is blown away, and therefore there's no chance that we would have detected something there? Or like, what's going to be the granularity here?
Okay, so granularity is still up for debate. One of the open questions we had in our discussion this afternoon was, what is the best ensign to use for the filter mount? So ways to compute the point source depth background evaluate that. You can also synthetic source injection. So that should catch things like ghosting, for example. The bright stars are, I would say, a special case because we know where they are in advance. And while this hasn't been incorporated in the pipelines yet, there are plans to model asking the area of reference.
So maybe I should broaden my question. It's more about they could be mass stars, they could be satellite trails, they could be all kinds of other things that make things hard to detect. So those are all in the flags image plane or in the mass plane, or recorded in some ways. Is that going to feed into your estimate of the selection function at whichever helix level you choose?
Yes. Okay. So right now, I don't know how much detail to go into. But so any of the artifacts get rejected from the coeds, and those are, like you say, regions with satellite trails, ghosts. Those are masked. Anything that has been masked and clipped, therefore not making it into the coads, that loss of depth in those areas is recorded in the heel sparse property maps for the coed detections, and those are built up by creating maps for the single epoch images as well. So sorry, I know I'm not explaining this in the most clear way. It's late.
I guess the fundamental use case here is we need to know at a particular point in the image, could an object have been detected, or to what depth, and that what's the level of reliability there? If there's a star there or a large galaxy, would we know that from these maps, or do we need to go back to the image and check?
I think the answer is all in resolution. There, at the finest, if you're curious about a particular pixel, you may have to reevaluate the answer on the coed or the image.
That may turn into a lot of computing for kind of solar system cases.
Take it over to Oh, okay. I thought you had a question.
Okay, so just a few announcements for tomorrow. So if you look at the schedule for tomorrow, the first thing is not a plenary, unlike the past 2 days. It's breakouts on inclusive collaboration. So I wanted to just briefly give people a sense of what's going on with that. So first of all, just a reminder, we provided some pre-reading. These are pretty concise, like 3 sort of 1 to 2 page readings that are really valuable. They're in the shared Google Drive and linked from various emails that you were sent before the meeting. But if you just follow the link to the Google Drive, they live in a folder, and I encourage you to check them out if you have not already. The breakout session will involve discussion of specific well-defined scenarios related to carrying out some of the science cases we've talked about collaboratively or collaborative software development, and how to make that happen in an inclusive way. And we've pre-assigned breakout groupings, intentionally sort of mixing across career stages and type of institute and so on. So at some point before that session, there will appear assignments for the breakout groupings, locations, and the actual link to the scenarios that the groups will go through starting at 9 a.m. So stay tuned for all of that, but I just wanted to give that quick forecast of how that's going to work.